suggest actually in the general discussion, because I'm sure that this topic will keep coming up, that we just ended on the possibility for life elsewhere in the universe, that we invite Professor Didier Queloz to make a statement on that, because I'm sure that will trigger more discussion on this topic. Didier, the floor is yours for a few minutes.
Thank you, Evin, for this kind of invitation. So I think we would agree, they all agree that after this series of great talks, I hope that we understand the universe is the most amazing and beautiful lab physicists can dream about, simply to test the limit of our knowledge on fundamental concepts such as time, space, and matter, as well as to discover new things. And for example, we have the famous dark energy, but there may be more new things that we may find in the universe. What I'd like to share with you in this short communication is that recently, I think we've started a new chapter that is looking like some sort of 21st century extension of, let's call it Copernicus revolution, the origin and prevalence of life in the universe. We are in a situation where we can really ask ourselves, what are the conditions for life to start and to evolve? It happened on Earth, but why not elsewhere? Why the universe produced life? It doesn't have to. Why does it mean to be alive? Is life massively present in the universe, or are we just a unique episode of Sherlock, doomed to disappear with our sun exhausting, when our sun will be exhausting its hydrogen fuel and will expand and engulf us? We all have to admit that these are one of the greatest existential questions, so challenging that we don't have much answer yet. Well, we're living, I believe, an extraordinary moment in our history, where a couple of spectacular scientific breakthroughs in different directions are bringing us an optimistic and fresh perspective that modern science is within reach. Deliver answer about why do we have life on Earth, and is that unique? Well, first, following my colleague's Karen Auberg talk, I think it's pretty clear that astrophysics is detecting and characterizing an increasingly numbers of exoplanets, bringing more and more information on the physics, chemistry, and for some of them, the surface conditions. Well, second, the planetary science is exploring in detail solar system objects, and we have a robot right now on Mars, and we'll be bringing pristine samples back on Earth. Well, think about that, and within the exceptions of some interplanetary dust from comets, the last time we did that was 50 years ago, when we brought samples from the moon. And third, organic chemistry has recently made fascinating progresses on the reverse engineering of the origin of life on Earth. And I'm pretty sure you'll have a better glimpse with some talks of my colleagues in the following days about what this science has been doing and progress. But let it face it bluntly, individual progresses in each of these disciplines does not guarantee that we shall solve the core problem. A growing number of scientists working at the forefront, and some of them are here in this room, are absolutely convinced and completely, let's say, aware of the intrinsic difficulty to develop a deeper overall understanding without broadening our knowledge baseline with a step change. I really say step change here in our collaboration model. Various groups of scholars and institutions are responding to these challenges and are developing new structural efforts to deal with its interdisciplinary challenges. Just repeat that, because I think this is the key here, the interdisciplinary challenges, and to create functional bridges with other fields. There are simple ideas that different disciplines looking from different perspectives can creatively operate together, and then filling critical knowledge sitting just in the boundary to enable the better exploitation of opportunity. The famous stories of low-hanging fruit in physics and in other fields. Similar line of thoughts are being developed as well, and it's worth to be noticed to address other very complex multidisciplinary challenges we're all aware of, such as global warming and AI revolutions. I humbly recognize that the question of the nature and significance of life transcends the traditional boundaries of natural science itself. For this purpose, for example, at Cambridge, in a collaboration with the Center of Theological Inquiry in Princeton, we have included art and humanities studies in the core activity of the recently established Leverhulme Center for Life in the Universe. Our goal will be to encourage philosophy, literature, and theology to actively engage and challenge concepts, as well as to bring in philosophical perspective. I'm not hiding to you that this is a broad and extremely ambitious agenda, but significant prestigious research and teaching institutions in the world have responded to these challenges and are clearly established center which is well supported. I believe we're all convinced, all these centers and people of these centers, that collectively we are establishing not only a new knowledge, but also some kind of legacy about cultivating a new generation of researchers, increasingly familiar to operate in a more flexible and interdisciplinary environment, with this strategical vision to establish a long-lasting pathway that will eventually lift the veil on one of the greatest mysteries of the universe. I thank you for your attention.
Thank you very much, Didier. And I think now we have all the ingredients together for a good discussion on this topic. So I invite indeed academicians to comment on that. Yes, please go ahead.
Thank you. I just have a quick question for Karen. I just want to understand the definition of habitable. Is it habitable for the type of life forms as we know them on our precious Earth, or could it include other forms of life? And Michael, the satellites that are protecting us from watching our stars, any other inconveniences beyond not being able to watch them? To watch the stars. Thank you.
No, perfect. Thank you. Oh, thank you for that question. It's a little bit of both. So we have good chemical reasons, and Didier sort of alluded to them, to thinking that the most likely form of life we are to find in the galaxy will be water and organic based. Water turns out to be a rather unique solvent for chemistry, in that it can dissolve both a number of small organic molecules as well as inorganic ones. But it's not the only possibility. People have speculated about hydrocarbons as solvents, maybe on very cold planets or moons, as we have in our own solar system. But still, most likely water, most life will be water-based. So if you have to sort of limit yourself to places to look at, you would look where you can have liquid water. Then if we turn to the organics part, carbon is just very special in the number of bonds and the sort of chemistry you can have with carbon at the center. And we see that also in our galaxies, or like far away from any sort of Earth life bias, that most molecules that we detect are organic in nature. So then it seems like it's also natural to think that any chemical life would be organic as well as water-based. But I would say organic for sure, the water, I think probably most, but maybe there are ways that chemistry can turn into biology that would use some other solvent. But it's not as Earth biased as one might think when first looking at it. It's more a chemistry thing.
I have at least 5 people lined up for questions. So let's first go on that row. Helen Blau, and then that. We have that, and then we have...
Question for Amina or Karen, and that is, what are the biggest threats to our sky, and what can be done to preserve our sky?
Let me take that. So, so there are a couple of things. So one of them is all of these constellations of satellites, which are affecting astronomical observations, particularly if you have a very wide field. There is going to be an increase, I think, of a factor 10,000 in number of satellites that will be crossing the sky. So that prevents, say, astronomical observations in the optical, but also in the radio. They are actually affecting the ability to measure the signals that we're trying to measure are very, very weak. And so they introduce noise such that it's much harder to detect those signals. I think that is from the astronomical perspective. The other thing is light pollution, right? So how often can we observe the sky in a dark place? And the effect is not only, say, observing the beauty of it, but also on on nature itself, we see the effects of light pollution also on animals, on vegetation, and so on. So there are many, the impact is large.
Add to that a little bit with my hat on as past president of the International Astronomical Union, that this is indeed a threat to science, a threat also to humanity, preserving the dark and quiet skies. Of course, these satellites also have benefits for humanity. They bring internet, especially to the poor and developing parts of the world, where internet is very much needed also for education. So it's a delicate balance that we are trying to interact with the companies to mitigate. So we cannot prevent the launch of all of these satellites, but we can try to mitigate their effects that they have, both on science and society. Yeah. Good. Yes, please go ahead.
My question.
Okay, go ahead.
Yes.
And then we'll go.
My question is about this primordial interstellar soup. And it reminded me the first time when I started as a postdoc, an older man came and sat at our table, and he said, "Do you think DNA could have come in a meteorite?" And I said, "Who's that guy?" It was Francis Crick. So the question is, the organic substances you have there, could they have amino acids or nucleotides or things of that complexity just running wild in the universe?
I'm going to say that's the nature of my question as well. Can DNA replicate other than in a water environment?
I will start with the interstellar soup, and then there might be people actually are better to answer questions about DNA replication than I am. So the short answer to these basic building blocks is yes. You could form amino acids and sort of small sugars and sort of the backbone kind of molecules in space. One of the pieces of, some of the pieces of evidence for that is that we have amino acids in comets, and we have a lot of them in meteorites. So these are things that formed outside of planets. Many of them probably date back to these interstellar clouds that I was showing. Now, when you try to make bigger and bigger molecules, there's sort of two ways to do it. One is to do combustion-style chemistry close to a star, and we do see the effects of that. We do see these very large organic molecules in space, so-called PHs, or polycyclic aromatic hydrocarbons. The other way is to sort of build up from smaller molecules, from amino acids, from RNA, DNA backbones to larger molecules. The latter is difficult when you're at very low temperatures. It's very slow. And if you're sitting in an ice instead of in some sort of liquid, there are probably some limitations of how many molecules you can bring together. So I would say definitely yes to the building block, but for these very large molecules, talking DNA, RNA, I think you most likely need a planetary environment for that, where you have a liquid solvent to form them and replicate them.
Good. Didier, you want to add anything for you about this?
Is from the physicist perspective, I think there is a couple of puzzling facts. I think the fact we are built on 20 amino acids, you don't find these 20 amino acids in the comet. There's only a few of them. So why these 20? There's another element, which is simply what I call resource hunting. When you do the chemistry, I mean, when I talk chemistry with my colleague chemists, they keep telling me chemistry always happens. There's nothing can prevent chemistry to happen. So life is competing against plenty of chemistry. So the question is, do you make life or do you make shampoos? And that's why you need some kind of a pathway, an optimal way to just drive the system into life. And that is part of the habitability, and that's part of the conditions for life. That can happen maybe in other solvents than water. But water is everywhere in the universe. Why do you make your life more complicated?
Good, yes. In fact, I remember very well, I was sitting here in this room in 1996, and Christian de Duve was here, and we had a similar discussion about the origin of life, and he said, well, chemistry will find a way to do it. And so that has always stayed with me, but you're very right that we also need some of the physics to get this there. So the final question then to Bishop Barron. Please go ahead. And then I'll ask maybe also my co-chair, Martin Rees, to also make a few final comments on this session.
Thank you very much for that. If you excuse a philosophical question, I was struck by the fact that I think in 3 of the 4 presentations, the word beauty was used, and Professor Erberg especially at the end. Aquinas' beauty is the splendor of form, so the splendor of intelligibility. Just curious, maybe to all the speakers, what conclusions would you draw of a more philosophical nature from the beauty of the data you're presenting to us?
Who wants to start with that? Amina? And maybe Michael wants to add a couple of words to that. We have to keep it brief because we're running already into our coffee time.
The reason they might
And maybe Didier.
Touch. It's amazing to actually have the data and you make a discovery of something that's really big and beautiful that actually makes you feel very small and humble. And that is something that stays with you.
Yeah, I think beauty comes in various forms. So if you measure something which is exactly as predicted, then that theory is beautiful. And it came, I mean, case of the general relativity came from Gedanken experiments where he just thought, does all objects fall in the same way? And just that process from that sort of inspiration to what we can test today, that is beauty. And of course, as astronomers, we also know, and physicists as well, if the net fundamental constants would be slightly different, the universe that we live in would be completely different. And whatever the answer is, whether it's multiverses or creation, I don't know, but it makes you think.
Good. Thank you very much, Martin.
Yes. Thank you very much. I think we've had a series of really inspirational talks. So thank you to all the speakers. Just 2 comments. First, we've realized how much we owe to observational developments, but computers equally so, for analyzing 2 billion stars discovered by Gaia, and also incidentally for allowing us to do simulations. We can't do real experiments. We can't crash galaxies together in the way that particle physics can crash atoms together, but we can, in our virtual world of a computer, learn a great deal about how this happens, and that's been very important. My other final point is simply that the likelihood of life is still a huge uncertainty, as we've heard. We may, from James Webb and from the European Large Telescope now under construction, get some spectroscopic evidence for life on nearby exoplanets. But also, someone mentioned the possibility of life under the ice of Enceladus, a moon of Saturn, or Europa, a moon of Jupiter. And if that could be discovered, that would be momentous because it would show that the origin of life couldn't be rare. If it happened twice independently within our own solar system, then that would tell us straight away that the galaxy was teeming with life. Mars, incidentally, may not be so compelling because life could go from Mars to the Earth and maybe vice versa. But looking for life elsewhere in the solar system with an independent origin would have huge cosmic importance. Thank you very much.
Good. Well, this ends then this session. I think another theme that we have seen is collaboration, how important it is to work together with different disciplines, but also to work together with different nations, with different cultures. Bringing people together towards a common goal is also bringing peace and prosperity and development to all of us on our little beautiful planet. I thank you all for your attention. And thank especially the speakers and Didier for all of their wonderful contributions. Thank you.